Hello, everyone. Thanks, Sebastian, for the introduction. Today, we know that many state-of-the-art models in AI are learned by minimizing non-convex loss functions. So let's consider the following non-convex optimization problem. Our goal is to minimize a function f under a parameter space k. We know that the most straightforward way of doing this is to run gradient descent. But if we initialize gradient descent at different points, the algorithm can converge to different solutions. And some of these solutions are locally optimal but globally suboptimal. One of the major challenges of non-convex optimization is how to prevent or how to escape such suboptimal local minima. Although escaping all local minimum is an NP-hard problem, we expect the algorithm to be able to escape certain poor but shallow local minimum. So as a motivating example, let's consider empirical risk minimization. We assume that empirical risk is pretty bumpy, spiky, contains poor but shallow local minimum. But we assume that the population risk has a much nicer shape, and all of the local minima of the population risk are global minimum. So this is just a one concrete example. The question is, can we find an algorithm that executes on the empirical risk, but guarantees to find optimal solutions of the population risk? As a starting point of our study, let's consider a simple variant of classical gradient descent. At every iteration, before performing the gradient step, we inject an isotropic Gaussian noise into the gradient. You can imagine that by carefully controlling the scale of noise, the algorithm will be able to escape certain local minimum. This is confirmed by the following example. I initialize the algorithm in the neighborhood of a local mean and start running it. You can see that after struggling for several iterations, the algorithm eventually escaped the basin of attraction of the local mean and eventually descend to the global mean. So this is one successful story. One caveat of this approach is that we have to pay attention to the choice of step size as well. For example, if the step size is chosen small, such as eta equal to 0.01, then suddenly the algorithm loses the ability to escape the same local mean. The reason is that the noise that we inject into the gradient are zero mean and mutually independent across iterations, so they can cancel out. If we use a too small step size, then the noise will cancel out too quickly before the algorithm makes sufficient progress in escaping the local mean. So we cannot choose too small step size. On the other hand, if we use a large step size, then we may lose the stability of gradient descent. The algorithm can overshoot and fail to eventually descend to the global mean, even after escaping the local mean. So how can we preserve the stability of gradient descent and at the same time preserve the power for escaping local minimum at the same time? One answer to this question is called a long-driven Monte Carlo algorithm. Comparing to the previous algorithm, here we multiply a factor 1 over square root of eta to the noise. And by this factor, we know that if eta goes to 0, then the noise will dominate the gradient, which enables the algorithm to escape local mean even with very small step size. There's another hyperparameter t that controls the magnitude of noise. I call it the temperature parameter, because in a continuous version of LMC, called a long-driven diffusion process in physics, this parameter t has the physical meaning of a temperature. If I replace the exact gradient by the stochastic gradient, then this gives the stochastic gradient long-driven dynamics algorithm. This is a generalization of LMC, because if the stochastic gradient is equal to the exact gradient, then this reduces to the classical LMC. I'm going to focus more on SGLD in this talk because it is the more general version of the algorithm. At this point, you may want to ask, why do we want to multiply this square root of 1 over eta to the noise instead of other functions of eta? The reason is that only by using the scaling factor, the algorithm is able to converge to a non-trivial stationary distribution whose density function is proportional to e to the minus f of x over t, where t is the temperature. So what does it mean? It means that if you run the algorithm for sufficiently long time and take the parameter x, it will be a random sample from the stationary distribution. And if I choose 1 over t large enough, then the stationary distribution will concentrate to the global mean of f. This is because that the density function reaches the maximum when f of x reaches the minimum. This is also demonstrated by the animation at the bottom. You can see that as the algorithm runs, the density function of x continuously evolves until it converges to the global mean of f. This is an attractive property for non-convex optimization because as long as we can run the algorithm for a very long time, we no longer need to worry about the local optimality. The algorithm guarantees to return a globally optimal solution. Because of this good property, there are many successful stories of using SGLD for solving real problems. People find that the algorithm is useful in prevent overfitting and also improve the learning for very complex models like neural Turing machines or deep LSTMs. On the theoretical front, we want to understand how fast does the algorithm converges to the stationary distribution. Although the asymptotic convergence has been known for many years, it was until recent years that people have started to rigorously understand the non-asymptotic behavior of Lagrangian dynamics. So for convex functions, it has been shown that the mixing time of LMC is polynomial. But this is less interesting because we know that convex functions are easy to optimize in an optimization perspective. We're more interested in non-convex functions, but unfortunately, it has been demonstrated that SGLD or LMC can have an exponential mixing time for general non-convex functions. The complexity has exponential dependence, can have exponential dependence on both dimension d and inverse temperature 1/t. This is a bit disappointing because for most of the problems that we care about, they can be of high dimension d. And from the last slide, we know that 1/t should be chosen large enough to guarantee that the stationary distribution concentrates on the global mean. And exponential dependence suggests that the algorithm might be too expensive to use in practice. But this is not the end of the story. In optimization perspective, we don't truly care if the algorithm converges to the stationary distribution. What we really care is if the algorithm can return a good enough optimization solution to us, a solution that achieves a small enough function value. And in practice, it is often observed that SGLD can hit a good enough optimization solution much earlier than it converges to the stationary distribution. To see this point, let's consider this W-shaped function. I arbitrarily initialize the algorithm. You can see that the point of x quickly descends to one of the two global minimum, but takes a long time before it can climb up the hill again to reach the other global minimum. It means that the mixing time on this function will be long, but the algorithm is very efficient in finding one of the two best possible optimization solutions. And it suggests that the mixing time might be a better metric to look at than the mixing time if you care about optimization efficiency. So this will be the focus of this talk. We're going to formally study the heating time of SGLD to an arbitrary set, which we call the target set. If the target set is properly chosen, we're able to prove polynomial time upper bound on the heating time, whereas the mixing time can still be exponential. And we're going to demonstrate applications to non-convex empirical risk minimization. So before presenting the theoretical result, let's first introduce several notations that will be useful for the analysis. The first notation is called a function-induced probability measure. Given an arbitrary function f, we define a probability measure mu f, whose density function is proportional to e to the minus f of x. So here f is an arbitrary function. It doesn't need to be the objective function that we actually minimize. And I'm plotting three examples of the density function at the bottom. The second example is called the second notation is called a boundary measure. It is defined on an arbitrary function f and an arbitrary set A. Formally, it is the ratio between the volume of a shell outside of A divided by the thickness of the shell. But informally, you can just understand this quantity as the surface area of the set A. Enter the probability measure mu f. The third quantity is called a restricted jitter constant. This is the most important and central concept we're going to introduce in this talk. The restricted jitter constant is defined on a function f and an arbitrary set V. It is the minimal ratio between the surface area and the volume of an arbitrary subset of V. To help understand this abstract definition, let's consider the following claim. It says that the restricted jitter constant will be small if and only if there's a subset of V that is fairly isolated from the rest part of the parameter space. As a graphical illustration, let's consider a non-convex parameter space K and a set V inside of it. For this particular set, we can find a subset A indicated by the green color that is fairly isolated from the rest part of the parameter space. It is isolated because the surface area of A inside the parameter space is much smaller than its volume. So the connection between A and its complement is fairly weak. And as a result, the restricted jitter constant defined on V will be small. On the other hand, if we consider alternative set V that has two holes in this parameter space, it can be verified that all subsets of V are well connected to rest part of the parameter space, so that the restricted jitter constant will be much bigger. Now, having this informal intuition, let's make a more formal claim on the connection between this quantity and SGLD algorithm. We claim that the restricted jitter constant defined on function f over t and a set V, arbitrary set V, measures the efficiency of the algorithm for escaping the set V. Although rigorously proving this claim is non-trivial, it is not difficult to intuitively understand it. In our first case of analysis, the restricted jitter constant is small, and we can find a subset whose connection to its complement is fairly weak. So if we initialize SGLD in this set A, it will take a long time before the algorithm can find a way to escape. So it's not efficient. In the second example, the restricted jitter constant is relatively large, and all subsets of V are well connected to the rest part of the parameter space, so that no matter where we initialize the algorithm, it will be easy to escape, and the escape will be efficient. Apart from this property, there's a second interesting property of restricted jitter constant, which is called the stability property. This property says that if two functions are pointwise close or uniformly close, then the restricted jitter constant of them will also be close. Formally, if two functions f and capital F are uniformly close with threshold t, then the two restricted jitter constant defined on f over t and capital F over t should be on the same order. If you combine this relation with the last slide, which says that the restricted jitter constant is a measure on the efficiency of SGLD, we conclude that for two functions that are pointwise close, the efficiency of SGLD on these two functions will be almost equivalent. This is a useful property for our analysis because it allows us to run SGLD on one function and analyze its efficiency on the other function. And this can happen even if one function has many more local minimum than the other function, such as in this example. Another concrete example is when you assume f is the empirical risk and f is the unavailable population risk. Capital F is the population risk. At this point, we're ready to present a general upper bound on the heating time. For arbitrary function f and arbitrary target set u, the general theorem says that the heating time inversely dependent on the following restricted jitter constant. From the previous slide, we know that the restricted jitter constant measures the efficiency of escaping the complement set of u. And in fact, escaping the complement set of u is equivalent of heating u. So it's easy to understand why the inverse of this quantity is a measure on the number of iterations the algorithm needs to hit the target set. The general theorem reduces the problem of upper bounding the heating time to the problem of lower bounding the restricted jitter constant, and further reduces to studying the geometric properties of the function f and the set u. The theorem is important because it turns out that studying the geometric property of this function and the set is much easier than studying the trajectory of a stochastic algorithm like SGLD. So this greatly simplifies analysis. The remaining thing to do is to lower bound the restricted jitter constant. We have developed a set of tools in the paper for doing this, and here I present the final result. So one of the final results is that if the function is smooth and can be non-convex, and if we choose the target set to be the set of approximate local minimum, and choose a temperature that is below some threshold, then the restricted jitter constant can be lower bounded by something on the order of square root of epsilon. So this is large enough to guarantee the polynomial heating time. Finally, what if we combine the lower bound of the last slide with the general theorem and with the stability property? As the final conclusion, let's consider running an algorithm on a function f and consider a proxy function that is pointwise close to f. If the proxy function is smooth, and if the two functions are uniformly close, then combining the result implies that SGLD can find out approximate local minimum of the proxy function in polynomial time. So how do we interpret this result? Since the proxy function is arbitrary, we can imagine that it is a perturbation of the original function that tries to eliminate as many local minima as possible. The theorem says that SGLD is able to efficiently escape all local minima that don't exist in the proxy function. You can also see this from the picture on the right. Even if you're trying to minimize a function that has many poor local minimum, the algorithm can escape all of this bad local minimum as long as there's a proxy function that can eliminate them. And it converges to the unique global minimum of the proxy function in this example. The last slide doesn't specify any concrete form for the proxy function. But for empirical risk minimization, it's natural to imagine that the objective function is the empirical risk, and the proxy function is the population risk. We know that the empirical risk converges to the population risk uniformly as the number of samples goes to infinity. So combining this with the previous slide, we know that SGLD finds an approximate local minimum of the population risk, and it can escape poor local minimum of the empirical risk efficiently. If we compare this with stochastic gradient descent, we see that SGLD is more robust. Because for SGD to guarantee the same optimality guarantee, it must require both the gradient and the Hessian matrix to converge to that of the population risk. But for SGLD, it only requires the function values to uniformly converge, which can be satisfied under much weaker assumptions. Finally, we apply the theory to a more concrete problem, which is learning linear classifier under 0-1 loss. We assume that the observed labels are corrupted by the Massart noise. And this is a typical scenario where the empirical risk is pretty spiky and contains many poor but shallow local minimum, whereas the population risk is much nicer and only contains good optimal points. So using SGLD, we're able to improve one of the best known learnability results for this problem. Finally, it's time to summarize the talk. We're interested in SGLD because it is an asymptotically optimal algorithm for non-convex optimization. The issue is that the mixing time of the algorithm can be exponentially long for general non-convex functions. So this motivates us to study the heating time. And generally, we are able to show that the heating time depends on the restricted Jigger constant, which is a quantity that we define in this talk. By lower bounding the restricted Jigger constant, we're able to prove polynomial upper bound on heating time. One highlight is the so-called stability property, which implies that if you consider a proxy function that is pointwise close to the original function, then the algorithm is able to hit the optimal points of the proxy function and escape certain bad local minimum of the original function. As a result, we're able to show that SGLD is more robust than SGD for empirical risk minimization in general, and also for the concrete problem of learning linear classifier and a 0-1 loss. So that's all I have to say. Thank you. My feeling is that it is close to necessary, although I don't have a formal justification for that. On the other hand, we have some technique to lower bound that, but this techniques for lower bounding the restricted Jigger constant won't be tight. So what I know is that the lower bound is not necessarily tight, but this quantity itself, I guess, it is both sufficient and necessary.
Your Jigger constant is actually a worst case. If, for example, I have a lot of regions of absolute approximate minimizers. If there's one which is hard to reach, this is going to dominate the Jigger constant.
Yes.
Is there a way to make this average case with respect to some distribution of the initial point? Can you repeat the question for the recording?
Yeah, the question is the restricted Jigger constant characterizes the worst case. So is there a way to have an average case measure on the efficiency? That's a very good question. So I think that may, I don't have a definite answer, but in order to get an average case efficiency measure, we should probably consider the optimization. The initialization strategy. So probably by using some random initialization, we're able to do that. But the current analysis only applies to the worst case initialization. So I think probably thinking about initialization is a promising direction, but I don't have a definite answer to that.
So you mentioned that earlier that SGD would require the gradient, the empirical gradient, to approximate the true, the population gradient. Is this? We know that this is not quite true in convex optimization. Do you mean like some sort of theorem, or is it just intuition?
It's more of intuition. Yes.
In convex optimization, that's not.
Yeah, that's true. Yeah, in non-convex optimization, the reason that we really need this convergence is because we need a distribution of the empirical distribution of stationary points of the empirical risk to converge to that of the population risk. For convex function, we know there's only one unique stationary point. But for non-convex optimization, there can be many more of them. So that is the part where they're different and where we essentially need a convergence.
One last question. Yeah, so this is kind of reminiscent of simulation annealing. And so there's this critical parameter of the temperature and how you... So is there a schedule here for the temperature, and how is the schedule determined? Is it determined data dependent?
Yeah, so the question is, this is in some sense similar to simulated annealing. And naturally, one would imagine that we want to use a temperature that is high at the beginning and then anneal it to decrease the temperature gradually as the optimization goes. That's a pretty natural strategy in practice. In the theoretical analysis, we just assume a constant temperature. It doesn't change it. In practice, it definitely will help to have a changing temperature, and I think it's worth analyzing it.
Okay, let's thank Yuchen.